This is a Z80 computer which I've designed. It currently runs CPM, ZX80 ROM and a ZX81 ROM, so it can play ZX81 games. If you've seen previous videos of mine, then you will see in the menu system for this computer, it has MSX listed and ColecoVision, because the plan was to be able to run MSX and ColecoVision cartridges on this system. So I'm in the process of designing the board which goes on top of here, which has the peripheral board, and it'll control things like disk drives, audio ICs, and also display IC, which it will be the TMS9929, which is the PAL version of the Texas Instrument display driver, which goes in both the ColecoVision and the MSX computer. So in this video, I'm going to emulate this display IC, because I thought if I put it on my emulator first, I get it up and running, then I get to know about the chip, and also I can have something which will should actually run on the board once I produce the board and actually be able to test the board. So first of all, I'll demonstrate the actual emulator running using the TMS9929 emulated on the ColecoVision emulation. And after I've demonstrated playing some games on that, I'll go through the theory of operation of the chip, and I'll go through then how the source code of the emulator for the chip. So I'll start my emulator. So it comes up with the ColecoVision turn off and insert a cartridge, but I'll select the cartridge. And I'll show 4 different games, and each game demonstrates a different screen mode of the Texas Instrument display chip. So the first one, Golf. The title screens, it usually keeps up on display for about 10 seconds or something before it goes into the actual game. Golf uses graphics mode 1. So if I start a game, and to explain what graphics mode 1 is, so you see the aliens across the top of the display. They're only basically one colour each, so it's got a foreground colour and background colour for each of the aliens. So that's the abilities of graphics mode 1. But you notice that the actual player, the base at the bottom, is yellow and blue. That's because it's a sprite rather than actually using the background of the graphics mode. So sprites are overlaid on top, and sprites have 2 colours also, but the background colour can be transparent, so you can lay sprites over each other. So what they've done here is they've created a yellow part of that sprite and a blue part, and the rest of it is transparent, so you see through one sprite and down onto the next sprite. So you could even have 3 sprites and have a 3 colour shipped at the bottom. But the rest of the screen, you can see, is just it's just 2 colours. But if I come out of that game now, so the next game I'll demonstrate is Galaxian. So this is graphics mode 2. Now this one doesn't make you wait to start the game, it just comes up and you can actually just press 1 to start a 1-player game. And this is graphics mode 2. So whereas in graphics mode 1 a block of 8x8 pixels can only be one of 2 colours, but each row of that 8x8 pixels can be 2 colours in this particular mode. So for every row of the aliens, they could have a separate 2 colour combination, which gives a lot more colours per block. But it doesn't give you a complete autonomy over colours. So each row, like I say, is restricted to just 2 colours. This is quite one of my favourite games, the one game that I used to play all the time in the arcade. So if I come out of this and go into the next game. So the next mode is a mode called multicolour mode. So each pixel in this is effectively 4x4 pixels of the actual display screen. The best one to demonstrate this is the Smurf Paint game, because I can actually run a demo on this Smurf Paint game, and it will actually run through some screens itself, and I can describe what the screens are. So if I go down and go into demonstration, so you can see that they're very blocky pixels. And if you look at the Smurfs, they're actually a higher resolution. That's because, again, they're sprites. So the sprites of the Smurfs can actually be overlaid on top of the actual blocky color mode. But what you see in the background there is actually the resolution you can actually create in color mode. You can't get any higher resolution than that, but each block can be any one of the 16 colors available on the Texas Instrument chip. I'll go to demonstrate the last of the modes. So the last of the screen modes, it doesn't really demonstrate it particularly well, but because it's ColecoVision games, it's the only one I could find. Well, there's probably other ones as well. Pit stop, so it demonstrates text mode. Now this isn't text mode at this point, so if I select a game, the title of the screen that comes up here, so that's text mode, and it would just be up briefly. And text mode, you could only have 2 colors in the entire screen, so there it was white and blue, and you can only have text characters, but you can define the characters yourself, like you can define any of these graphics yourself. So you could have kind of graphic. You could play like a graphical game in text mode. It's just that you'd only have two colors to play with on the entire screen. I guess that's for like if you've got virtually no memory available to the display chip, and you want to just use it in a very basic system, I guess. Apart from that, I mean, because you could do text mode effectively on any of the graphics modes available, it would just take up a bit more memory because you'd have to define colors and positions on the screen and stuff like that. So this is a basic overview of how the display works within the actual chip itself. So if you wanted to program it, you have these tables which you can define, and the first one is the pattern table. So basically it's an 8x8 grid. Each character is an 8x8 grid that you can define, and so this is the same as you would have in a character ROM for like a TRS-80 or like an old 70s type computer or 80s type computer. Even the ZX Spectrum, some of the characters you could actually redefine, and it's basically the same as that. You just define each row of a 8x8 grid as hex numbers, and the name table maps each of those patterns into the actual display frame. So in the green grid area on this slide, it actually shows. Well, the actual display is 40 by 24, so 40 across by 24 down, and each of those elements within the frame has an entry in the name table, so you can actually map any of the patterns to any of those entries in the display frame. And then lastly, there's a color table which also maps onto the grid within the display frame. So basically it's a character display, but you can define each of the characters within the display as being one of 256 patterns. And then separate to that is a layer over the top of that display frame which holds sprites. You can have up to 32 sprites, and the sprites could be 8x8 or 16 by 16 pixels, or 8x8 magnified by 2, so each pixel is represented by 2 pixels, or 16 by 16 magnified by 2. But you can only select one of those modes at any one time, so if you want 16 by 16, you have to have that for all of your sprites, although it doesn't stop you defining an 8x8 sprite within the 16 by 16 grid. So that allows you to do some pretty neat tricks within the actual display chip itself. So you can actually have multiples of any of the tables. So here it shows multiples of the name table, each having reference to its own display frame within memory. And it can use the same, so here it's using the same pattern table between the two name tables, but you could have a pattern table for each of the name tables. But this actual slide, I'm just representing the way that a lot of games work, in that they'll have a display frame which is being updated, so it's not being sent out to the VGU, and they'll have a display frame which is being sent out to the VGU. So the one that's not being sent out to the VGU, the actual game is updating that frame, and then when the frame has been updated and is complete and ready to go out to the VGU, it then switches from the display frame to the update frame, and the update frame then becomes the display frame. So then you can clear the frame which is the old frame and start updating that, and that prevents display tearing from occurring. So it's generally known as double buffering, this method. So within the chip, because of the way it's constructed with these tables, you get that for free. But you can also use that for other things. So Centipede game on the ColecoVision, it actually uses this kind of method, but for going between player 1 and player 2. So on ColecoVision, in the system RAM, you only get 1K, but the display RAM has 16K, but the display RAM is tied to the actual display chip, so you can't really access it directly, but you can access it through the I/O system on the Z80. But what they do is, because the system RAM isn't really enough to hold 2 screenfuls of player information, they have one display frame for player 1, and they set that up and they put all the mushrooms in there. But when that player loses life, it switches to the other display frame for player 2, and they have their own setup of mushrooms and stuff. And that means that when player 2 loses a life, it can switch back to player 1's screen as it was when they finished their turn, and vice versa. And so that's the clever way, again, of them using the actual Texas Instrument display frame. And it's very versatile like that. So you could even use, you could even use 2 pattern tables, or say 4 pattern tables, and you could actually switch between the pattern tables, which is only updating an address in memory. And you could animate all of the patterns within that pattern table. So you could have animated characters just by having to update an address, rather than updating all the graphics information to animate those graphics. So again, a very versatile way. And just as the same with the pattern table, you can update the color table, so you could actually animate the colors on the display as well. So it's the way they put this together is actually very versatile for the actual time that the chip was being produced. So I'll go over the source code of the display driver for the Texas Instrument chip in my emulator. First of all, I'll go over the ColecoVision emulator, because it's just a quick thing to do, so you can get the context of how it's put together and integrated with the display chip. So the sound chip I haven't emulated yet for this, which is why you didn't get any sound in the demonstrations. Up here at the top, if you've seen my other videos, it's just configuration stuff for my emulator. I've got the single entry point if you're running on Linux or something, and then the multiple entry point if I'm running on a microcontroller. Sets up a display window which it's going to use. Initializes the Z80 part of the emulation, which if you want to find out more about that, that's in one of the earliest emulation videos which I've done. But then it does the TMS9929 initialization, and this it should be the same for all of the various versions of the Texas Instrument chip, because I'm not using PAL or NTSC here, so I think they should all operate exactly the same way. And I'm giving it a memory address which it can use for its 16K of display memory. I'm placing that just above the 64K that the Z80 can access. I then load the ROM of the ColecoVision, and then I have to set up a memory map for my emulator. And what I'm doing here is I'm making everything from 0 to up to the 64K boundary is read-only. Then I'm unwrite protecting one little bit of memory, which is the area where the RAM is. So everything in this emulation is going to be read-only apart from just the 1K of RAM. Then I'm setting up the callbacks for my Z80 processor emulation. So I have a callback for the clock, so every clock ticket gets a callback, so I can do stuff whenever it needs to be done. I have a reset callback, so I can take care of anything that needs to be reset at the same time the processor is reset. Then I've got a callback for the ColecoVision has a controller, and it has a port for keypad, and it has a port for joystick. So these ports are for actually switching to keypad or switching to joystick. So only at any one time there's only either the keypad enabled or the joystick enabled, and it switches between the two to actually read them. And then I have the 2 ports for the actual display chip. But there's also an alternate locations for the display chip as well, because only one of the game companies which I've come across going through the cartridges uses an alternate port number for the actual display chip, and I don't know why they do that, but all the other manufacturers seem to use a standard one which is there. But they basically map onto the same function, the same callback functions anyway. It's just mapping 2 ports to the same callback. and then I map the controller port, sound chip port, and alternate controller and sound chip ports. Again, that's the alternate, that's the manufacturer which uses different ports for its stuff for some reason. And then I go into start the execution of the emulator, and when that's finished, it just makes sure that it goes for a terminate process so that it can free up any resources which these things have allocated. So this is the reset callback, and it just calls initialization of the Texas Instrument chip, so that it can, so if the Z80 is reset, that the actual Texas Instrument chip is reset at the same time. And then these are the ports which actually switch between whether it's a keyboard or the joystick being read. And so I'm just changing the flag in my emulator here so that I can know which one's currently being read, either the joystick or the keypad. And then this is a sound chip callback, but they use the sound chip port for two tasks. So for the output, it actually drives the sound chip, but for the import, it uses it as a player 2 controller. So either keypad if it's on switch to keypad, or the joystick if it's switched to the joystick. And then the controller 1 has a port of its own, and on the input it's either reading the controller 1 keypad again or joystick again. And you don't see the Texas Instrument drivers down here because they're mapped to the actual driver itself. So we'll go through that in just after I've gone through this, and this is the last part of it. So on the clock callback, I detect whether or not the cartridge has been swapped, and if it has, then I load the cartridge into memory at the cartridge address, which is 8000 hex, and then I reset the Z80 so that it then starts up on that cartridge. I look for just a debug key press because there's no keyboard on this. The keypad and joysticks are handled above, so I don't have to do anything about that. I call a display frame update, so I'm actually calling the driver for the Texas Instrument here and just saying update the display frame. And on the ColecoVision, it uses the non-maskable interrupts on the Z80 for the display chip output interrupt, whereas on other computers like MSX, I think they use just the standard maskable interrupt, but on the ColecoVision they use the non-maskable interrupt, which is why I have this function in my driver for the Texas Instrument, so that I can actually do that integration here in my emulator and not assume it's going to be the maskable interrupts. And that's the ColecoVision emulation. And now I'll go through the actual Texas Instrument emulation. So even the Texas Instrument part of this emulation is actually quite simple. So at the top I'm just making places for the registers within Texas Instrument chip, so I can keep track of things like that and the different addresses which can get set up. It does the initialization of the Texas Instrument chip, and I set the VRAM address where it can go, and I'm setting it to make sure that it's write protected for the VRAM address so that nothing can overwrite it. And then I call the standard reset procedure, which I'm using for this emulation for the Texas Instrument, which does this. It just initializes all the variables to initial values and sets the memory to 0. Even though actually in the Texas Instrument chip itself, probably it wouldn't on reset, it wouldn't reset all the values in RAM to 0, but I'm doing that here. And default mode, I'm making graphics 1 and setting background colors and stuff. It doesn't actually do anything in the termination because there's nothing to clean up, but I've got this as a placeholder just in case anything needs to be added there. So in one of the registers, it allows you to enable or disable interrupts, and this is just a way of my emulator finding out if or not the interrupts are enabled or not, so that it can decide whether it's a non-maskable interrupt it wants to do for ColecoVision, or if it's a maskable interrupt it wants to do for MSX. And this is the VDP callback. So this is where it sets values and reads values from the registers. So here, if you read it, if you're reading, it only ever reads the status register. But if you're outputting, you can output to any of the registers. And it, depending on which register, it just sets up the values within the register itself here, within the appropriate register that it's supposed to be set in. And then it keeps track of if there's specific registers which have been changed, then it just keeps track of certain flags just to make it more efficient. Rather than doing these conditional things later on in multiple locations, it just sets up the actual mode of operation for the actual chip, whether it's in graphics mode 2, graphics mode 1, multicolor or text mode. It does the same for if you set the colors as foreground and background color, it just keeps track of them here. And also you can set the different addresses for the patterns and the name tables and the color tables. And so that does that here, so that, and this is just as I was explaining in the operation of the chip, you can actually just change the address to point to a different pattern table, and that's all it requires is like about 4 bytes or something of communication in order to change the actual patterns completely, or change the frame you're using completely, which is very efficient, rather than actually sending all the data to redraw another pattern table or another frame of data. And then this is the other thing it can do, is it can set a VRAM address for where it wants to read or write to in the VRAM. So you can actually read and write directly to the VRAM. And some of the cartridges do actually use the VRAM within the display driver or within the Texas Instrument chip for actual storing of game parameters, because it's only got 1K of memory, the ColecoVision. So I think it actually uses some of the VRAM address, not for actually display data, but for actually just storing game data in. And this is the other callback function that there is for the IO ports. And this one, so after the address has been set as described above, it can then either read a memory location or write a memory location in the VRAM. So that's all that does. And I think this is the only other function within here, and it's to handle display in a frame of the graphics depending on whichever graphics mode you're in. So it handles triggering an interrupt because we're doing a display of a frame, and it only does a display of a frame if it's flagged to be enabled to output a display of a frame to the VDU. And it goes, I've just commented here because it does the display in different planes of graphics. So on one of the chips you can actually combine your graphics with external video, so that would be the lowest plane that there is, and then there's the background color, and then there's the pattern table, which is what we're going to do here, which is the graphics, and it decides which graphics mode it's in. And it just has a simple display update, so it goes through the 256 pixels by 192 pixels, and it looks up how it should do from the datasheet, the pattern name, the colors, and then it just plots them. So like I say, it's an 8x8 grid of pixels, so it's doing 8 rows, and each row is a byte of pixels, so it's 8x8, and it's just sending those to the display. And the way it looks up the colors is slightly different for each of the graphics modes, so that's what you're seeing here is so for graphics mode 2 it's just doing the colors in a slightly different way and displaying the display in slightly different way, but each one of these just handles a different way for the mode. And this is multicolor mode, so all the modes are very similar because you'll see that they go 192 by 256. They stick to there's only one resolution, but even though multicolor mode is just like blocky graphics 4x4, so it's a 64 by 48 effective pixel grid, but really underneath that it's still using the 256 by 192 pixels. And then the last mode is the text mode. And again, it's done in kind of the same kind of way. And then the next plane is the sprites. So it doesn't display sprites in text mode. It displays sprites in all of the other modes, but it can't display sprites in text mode. And it goes through the 32 different sprites. But what it does first of all is this loop just looks for an end of sprite table marker. So if you only wanted to display 5 sprites, then the 6th sprite entry would be D0 for the YPOS. So it will only display as many sprites as there are in the table. And then it just goes through all of those sprites which are actually in the table that have to be displayed. And it just picks out, so each sprite has like a parameter. So you can set the XPOS, the YPOS, the ID of the sprite, which you're looking up for the graphics, whether or not it's 2 times magnification on the pixels, on whether or not it's a 16-bit or 8-bit sprite that you actually want to display. And so then it just goes through and displays them in this piece of code here on in the location of the display where it needs to display them in the color that they need to be displayed, in the magnification level they need to be displayed. And then there's a collision detection. I think I need to actually review this part of my code. I'm not sure if this is correct or not, but the chip also allows you to, so if any of the sprites collide, the chip will set a flag, so you can just check the flag to see if any sprites have collided. It won't tell you which sprites have collided. I don't think you have to work that out for yourself. But that's the actual emulation of the Texas Instrument chip. So programmatically there's not much there, but it did take a little while to go through all the data sheets and work out everything. And like as always, there's always 1 or 2 errors in the data sheets which like throw you a bit.